ml equals 3, ml could be negative 3, negative 2, negative 1, 0, 1, 2, 3. So each individual value for an ml is 1 alpha. If the ml is fixed, there can only be 1. Now we can ask you, how many alphas do we have if n equals to 4, n equals to 5, l equals to 3? Well, n equals to 5, l equals to 3. We can have n equals to 5, l equals to 3. We can have 5 ml. Okay. Negative 3, negative 2, negative 4, negative 1, 0, 1. No, the L, I mean, ML equals to 2L, that's plus minus L. That's a relationship.
Recently, I've been looking
Okay,
at
so when L equals 3, we have 1, 2, 3, 4, 5, 6, 7. We have overall 7. So how many alphas? If you do not, define ML, there are 7 alpha values.
see,
Negative 3,
good luck with
negative
the
2,
I know.
1, 0, and then 1 here, total 7. So if you don't show this number, there are 7 possibilities. But if you say ML equal to negative 3, there can only be 1. If ML equal to 0, there can only be 1. Yeah. 1, yeah. If ML is shown, it's one of those 7. If ML did not show, if you don't show ML there, with L equal to 3, you can have up to 7 each orbital calling exclusion principle, each orbital can only take 2 electrons. Well, that's the total number in this N. We're talking about one particular orbital. In N, you have 25 orbitals in there. You can pick up to 50 electrons in there. But in each orbital, you can only No, there's an example, step by step, example in chapter 6. So hot object, heat come out from the hot object equals to heat absorbed by the cold object. So C and the heat, that's the equation. So the mass of the sample is 45 grams, and the water is 100 grams. You have a different temperature. When the two are mixed, eventually you reach the same filter. The equal, no, that's the equation that we need. So it's a gas law plus the stock energy. All right, guys. All right, the other topic that we want to cover in chapter 10, before we move on to the next chapter, is what we call the valence bound theory. So we would now, by now, we know how the electrons are distributed, not only within a particular atom, but also within a covalent bound molecule. And we can actually make all the predictions about electron distribution, we can make predictions about the geometry and all that. Yet, every time when you develop a new theory, you have to make sure that that theory will actually fit into the theory that we have already developed. And if there is a contradiction, we have to make modifications there. Now, valence bound theory is one of those modifications that we need to make based on what we understand in terms of electron distribution versus what's actually happening, what we observe in the laboratory there. So in this particular case, we're going to look at the valence bound theory and talking about orbital hybridization. When you have two electrons on the different sublevel, say the 2s electron versus 2p electron, based on the old theory, they're supposed to have slightly different energy. Now, if they have slightly different energy, that means they are different. If they're different, when they are being used to form chemical bond, they are supposed to form different types of chemical bond, in terms of bound length, in terms of bound polarity, even for that matter, and then bound angle there. However, that is not what observed in the laboratory. So we have to make some modification to the old theory there, and this is where the orbital hybridization comes in. Now, orbital hybridization is a fairly complex theory. All we need you to know is to remember the first three, the simplest forms of hybridization, namely sp3, sp2, sp. Okay, and be able to, based on the Lewis structure and focusing on the central atom there, be able to make predictions about the hybridization pattern on the central atom. Okay, so talking about the covalent bonds, we say, well, when two atoms come together, they share the electron. Well, that's a fairly general statement.